A very warm welcome to you all on behalf of Propagation Institute for Advanced Studies. We are happy to welcome you for the today's session under the Curious Mind series, a weekly initiative which focuses on space science, learning, and interaction. Propagation Institute for Advanced Studies is an educational institute dedicated entirely to space science education. We function as a school for space science, working with the school, colleges, and students to build scientific thinking, curiosity, and research-oriented learning. If you are interested in space science, whether you are a student or someone exploring this field, you can learn more about admissions and learning opportunities by visiting our official website. Relevant links will also be shared via your registered email. Now, we have our flagship program. It is related to the academic initiatives which we will be launching very soon. The Cosmic Researcher Program, a year-long space science learning journey, which includes expert-led sessions, research-based projects, and hands-on scientific activities designed to help learners develop a strong foundation in space science. I would like to share my screen just a sec so that you can have a look at the website. Here, this is the website where you can go in the outreach and the events. Over here, you can see the different parts where you can go and learn about the Cosmic Researcher Program. It can include basic models such as the astronomy, advanced astronomy, rocket science basics, and etc. So I would just stop sharing and continue with my introductory part. Now, the Curious Mind series. This session is a part of Curious Mind series where on the weekly platform where we organize interactive expert sessions, scientific talks, and workshops, giving learners the opportunity to engage directly with researchers and professionals. Today's session is Older Than the Sun, the story of pre-solar grains. This session will be presented by our speaker, Dr. Manish N. Sanghani. He is a planetary science researcher working on pre-solar or stardust grains found in primitive meteorites. He completed his MSc in physics from Sardar Patel University, Gujarat, his PhD from the University of Copenhagen, Denmark, and a postdoctoral fellowship at Physical Research Laboratory. He is also actively involved in STEM education and science outreach. We are delighted to have you, Dr. Sanghani, with us today. Without further delay, the mic is over to you.
Hello, good evening, everyone. And thank you so much, Amoli ma'am, for giving such a nice introduction. And so I would first congratulate this Propagation Institute for Advanced Studies to create such a nice platform so that starting from the school students to the masters and researchers can interact with each other for the benefit of all. So today, as Amoli ma'am says and this slide says, so I'm going to talk about the story of pre-solar grains. So this is kind of you can say my journey also, my journey of a PhD or research. So I will immediately start. So these the first slide you are seeing is my collaborators.
Sir, the slide is not visible. Kindly share your screen.
The slide is not visible. Okay.
No, sir.
Just wait. Yeah. Okay. Is it visible now?
Yes. Yes.
Okay.
Yes.
Okay. Sorry. Yeah. So from the slide one, you can see these are my different collaborators. Okay, yeah. So I have worked with PRL and several other institutions across the globe. Okay, this is the plan of my talk. First, I'll introduce our solar system. This part is very well known now. And I'll dive into meteorites and then presolar grains. This will be the technical part, the third one, where I'll briefly explain the extraction of presolar grains from the meteorite samples, and then how do we do sample preparation and analysis and all those things. Then I'll share some exciting cases during our research, our group's research on presolar silicate grains basically. So basically they are from AGB stars, nova and supernova. So these three stellar sources basically from where we are getting these silicate grains. And then I'll discuss about the formation and alteration or change in the structure or chemical composition of the silicate grains based on their structural and chemical composition. And then I'll just briefly discuss the takeaways, and then we can have interaction with the audience. Okay, so we'll start with the this cartoon. So this cartoon says that there is a somewhere in the space there is a massive cloud of gas and dust, which could be either beginning of a new solar system, or it could be just a lot of gas and dust. So as we all know that. So this slide explains how our solar system formed and what is the present scenario. So this part is very well known. I'll not go into much detail. Plus, but it is very well known by from the theory and various observations that our solar system was formed about 4.6 billion years ago from a giant molecular cloud of gas and dust. So the cloud which was there, I mean the gas and dust was there. It was compressed due to the gravitational forces, or there could be a chance that a nearby supernova explosion might have triggered the cloud collapse, which formed, which collapsed to form our solar system. So yeah, so then we have this protoplanetary disk because the sun, the proto sun is in the center, and then the all the mass, the remaining mass is turning around the sun, and then we have the different phases, and then finally we have this present solar system where we have the sun at the center, and then 8 planets excluding Pluto now. So this is how the timeline of our solar system formation. So from 4.6 billion years ago, when the sun formed and the cloud collapse, till now, where we have different planets and asteroid belts and many things. So, but how do we know? So we have several things to support this theory. The theory is called as nebular hypothesis, which is widely accepted. This a theoretical model for the formation of solar system. And then we have now observational astronomy, where we have these several telescopes. It is very exciting phase, I will say, where we have Hubble Space Telescope, and we have Atacama Large Millimeter Surveillance Area, and we have space telescopes. There are a lot of information of different parts of or different regions of space where we can see many different things, and then we can correlate it with the our solar system. And then we have meteoritic records. So we have different. I'll talk this part into details in the next slides. So, okay, so we have these planetary disks. So how do we know that that this nebular hypothesis is correct? So we have this different protoplanetary disk observations from different space telescopes. This one on the left side is the Hubble Space Telescope image of different protoplanetary disks, and in the right we have this. In the right also we have this Hubble image where you can see the sun in the center, and then there are different regions around the sun where you can also see the gaps, and these gaps are where the planets are forming. So these are the protoplanetary disks. Also we have this ALMA observations of the protoplanetary disks, where the sun in the center, and then there are disks and then gaps and everything that you can see. These are the images created from the millimeter and sub-millimeter wavelengths. So, so from this we can say that these are the different part of the galaxy. So, like for example, there is a star called HL Tau, and then we have TW Hydra, and so these things from these observations we can say that we can correlate it with our solar system. Okay, and then we have these meteoritic records. So this in this cartoon you can see that there is a sun and then there is a protoplanetary disk where different dust grains and inclusions and chondrules and different things are forming. So what are they? Basically, so the first forming solids are known as the calcium and aluminum rich inclusions in our solar system. So these are known as CAIs, which we found it in various primitive meteorites. And then we have chondrules. So these things, the CAIs and chondrules are very first forming solids in our solar nebula, in our solar system. And then we have different dust particles and planetesimals they are forming. And then so this protoplanetary disk is a very dynamic environment where the dust particles are clumped together, and then crystalline and refractory dust are forming, and then they also jump into the other parts of the disk, and this is how this scenario is there. And then we have these meteorites called primitive meteorites. These are the chunks of or the fragments of asteroids which we have. We know that we have the asteroid belt in the. I'll go back into the. Yeah, so we know that we have the asteroid belt between the Mars and Jupiter orbit. So these meteorites are the fragments of those asteroids, and in those meteorites we are finding this calcium aluminum rich inclusions and chondrules and these things. And yes, so we have different isotopic systems. For example, we have aluminum and magnesium isotopic systems people have studied within the CIs and chondrules. And then we have uranium and lead dating and lead dating to tell that when exactly our solar the sun and the CAIs and chondrules formed. And this from these experiments from their projects, from these chronometers, we know that our solar system, or you can say the CAIs and chondrules, formed about 4.56 billion years ago. So these are the primitive these are the records from the meteorites. Okay. Now, what are these meteorites? We all know that these are the fragments of asteroids and comets. They are hitting the Earth's surface, so we can find them. We can get them from different places on Earth, like Antarctica, like Northwest Africa, Saharan Desert, and various other parts. So yeah, we can collect those samples and then we can analyze them in the laboratory, which give us very detailed insights into many different solar system processes and many other systems, we can say. So there are various types of meteorites. I will not go into details of the types of meteorites, but basically they are stony or iron or stony iron meteorites. So basically they are either they are differentiated meteorites or they are stony meteors. So when the meteorite is a differentiated, so it is a core like our planet, which is a differentiated body, where it will have a core where iron and nickel will be clumped together, and then there will be several layers of different materials. And these meteorites give the clue to early solar system processes, as we all know. Okay, so from these different types of meteorites, we have something called carbonaceous chondrites. So these are very pristine meteorites. What does it mean by pristine? That means they are not altered. They have not changed their composition from their initial phase. So these carbonaceous meteorites or carbonaceous chondrites have high amount of carbon, and they have hydrous minerals and water. They have some amount of metal and silicates, And then they have these pre-solar grains, something called pre-solar grains. So what are these pre-solar grains? Now I'm getting into details of these pre-solar grains. So these are basically the dust particles which are formed in the stellar winds and in the ejecta of stellar explosions like AGB stars and supernova. And then they incorporated into the asteroids which were forming in the early solar nebula or in the early protoplanetary disk. And they are right now, they are found within the meteorite samples. And they have unique isotopic compositions. That means, how do we know that they are pre-solar grains? They have different unique isotopic compositions, which is very, very different from the solar system samples. So if you go and collect any solar system material within the solar system and then do isotopic analysis, like for example, we measure 16 oxygen, 17 oxygen, and 18 oxygen. These are three oxygen isotopes. So if you measure the isotopic analysis of any solar system material, which is something which is one fixed figure. Now if you analyze the pre-solar grains, their isotopic composition is very, very different. Like I'll go into in the next slides. I'll show you how they are different. They are different from 15, 20 times or even more than that. Okay, so from these unique isotopic compositions, we can say that these are not a part of our solar system, but they were formed in the supernova or in the AGB stars even before the sun was formed, even before our sun was formed, right? Or our solar system was formed. So these are the part. So these are formed in the AGB stars and supernova, and then they incorporated in the molecular cloud, which collapsed to form our solar system. And now they are now we can find them in the meteorites. I hope this part is clear. Okay, so again, so these are the stellar outflows. So pre-solar grains basically originate from the stellar outflows from the giant stars, and they incorporated in the giant molecular cloud, which collapsed to form the protoplanetary disk. And then so in within the protoplanetary disk we have asteroids and comets, right? And then so these pre-solar grains traveled from the ancient stars like supernova and AGB stars or RGB stars or red giant or asymptotic giant branch stars. They somehow survived the dynamic environment of the protoplanetary disk, and then they incorporated into asteroids. Now these asteroid fragments, which we get it like sample return missions, or like we have meteorites on Earth, or we have interplanetary dust particles. And then finally, we get it from within the meteorites. We do it in a laboratory analysis and then find these pre-solar grains. So this is how the journey of pre-solar grains. So this journey of pre-solar grains is a billions of years journey, right? So for example, our solar system is 4.5 billion years ago, and these grains are even older than the sun. So this journey is about billions of years, and then we have these tiny pre-solar grains. How tiny? So they are from a few nanometers to several microns of pre-solar grains. We get it in the in our samples. So these are the red giant and asymptotic giant branch, just to say. Okay. Now, how do we find them from meteorites? What are the processes that we find them from meteorite samples? So there are mainly there are two processes. One is the chemical separation. So you know that the meteorites are basically a lot of silicates, right? So we have to dissolve more than 90% of silicates and metals and other things to get the refractory pre-solar grains. So the refractory pre-solar grains are silicon carbide and oxides. So we have to use different. I'll go into the next slide. Yes. So we have to. I'll not go into detail, but this is a chemical protocol. So we have to use HF and HCl and other kind of acids to dissolve almost all the silicates within the meteorite to get the refractory silicon carbide and oxide grains. So this is a chemical protocol which is a very cumbersome process. So it is something like to burn all the haystack, the big haystack, to find a small needle, right? So so because the presolar grains are just parts per million within the meteorites. Okay, so yes, and the other procedure to find the meteorites within the meteorite sample, presolar grains, is the in situ mapping. And the mapping is done using a very highly sophisticated instruments called mass spectrometers. This is just an example of a sample, which is the 16 oxygen image or 16 oxygen map of different regions of the meteorite sample, which we have used. Okay, so to go into the in situ mapping of presolar grains, to find the presolar grains. So, for example, this is the meteorite which we have used, which was the Ishievo meteorite, which we studied. This is a Russian meteorite, and then we have to cut the meteorite into small pieces and then make this kind of a thing, like a small chip, and then we have to mold it within the epoxy. So to make this circular sample or thin section, and then we have to polish it and conduct. Then finally we have to do a conductive coating of with some nanometers before putting it into the instrument, into our instrument called the secondary electron microscope, scanning electron microscope, or the mass spectrometers. So this is just an overview of the sample procedure, preparing sample preparation. Okay. For example, this is one meteorite sample, Northwest Africa 801. So I have used two different meteorites. One was the Ishievo and another one was this one, Northwest Africa. And then we have used this, yes, so we have used this NanoSIMS, which is called the nanoscale secondary ion mass spectrometer, where primary ion beam hits the meteorite sample, and the secondary ions which are ejected from the sample, they are collected in a mass spectrometer. So we can get different isotopes at different uh, at different detectors. Okay, so this NanoSIMS is a very highly sophisticated, high mass resolution and high spatial resolution instrument, which the spatial resolution can go down to 50 nanometers, right? So we can even target a 50 to 100 nanometers smaller presolar grain. Okay. This is just an example of our scan of our sample analysis, where this square you can see, this is just 20 by 20 square micron, and we got this. This is the what this is the grain which we analyzed from the first sample. So this is the first or second pre-solar grains that we have identified within this sample, Ishievo sample. Okay. So there are, as I told you in the previous slide, there are various types of pre-solar grains. Basically, they are silicon carbide. We have graphite. These both are and nano diamond, which are the carbonaceous pre-solar grains. And then we have silicates and oxides. Sorry. And I studied silicate grains. Why? Because they are more pristine. Why? Because to extract the presolar silicon carbide and graphite and oxide grains, we have to use acids, right? So acids, what does they do? They etch the surface of the sample or the presolar grain, the surface of the presolar grain, or sometimes there is a chance that the chemical composition might alter. There is a chance, right? So I studied silicate grains, which are more pristine because we are finding them by in situ ion imaging technique. So we are not using any kind of harsh acids or any kind of chemicals. So they are more pristine, and they are not affected by any chemicals, and they have various parent stars. Okay, so I'll now discuss. They are the different stellar sources of silicates and oxide grains, which we have studied. Okay, so this is a plot from my first paper during my PhD, where we have plotted 17 over 16 oxygen on the y-axis and 18 over 16 oxygen ratio on the x-axis. And we have classified our oxygen-rich presolar grains into 4 different groups. For example, group 1, you can see that the 17 over 16 oxygen ratio is very high as compared to the solar system ratio. So this dashed line represents the solar system 17 over 16, and this line represents the solar system 18 over 16 ratio. And whenever you analyze any solar system material, as I have said in the previous slide, it will fall in just a small circle here. Okay. But as you can see, the presolar grains, the oxygen isotopic composition seems far, far different, several orders of magnitude different from the solar system sample. So this is a solar system 17 over 16, and you can see this particular grain, this red dot, it is about 15 to 16 times higher than the solar system. Similarly, this Ishievo 6, this grain, this is a group 4 grain coming from supernova, which is about 16 times, again about 16 times the solar ratio, solar 18 over 16 ratio. And this cannot be explained by any kind of solar system processes. This cannot be explained. If you take any other, any solar system process, it cannot explain this much deviation from the solar system standard. And then we have to think that these grains are formed in the giant stars before the sun was formed. Okay. So we have analyzed 2 different samples, and we have got about 33 pre-solar silicate and oxide grains. This is the first part of my study. Okay, now I will share several interesting cases. As I have told in the previous slide, I have shared in the previous slide that these silicates and oxide grains are from AGB or red giant or asymptotic giant branch star. So like a sun-like star, but having higher mass. And then they are also coming from nova or supernova explosions. Okay. So this first part, I'll discuss about an AGB grain, a grain from the AGB star, and why this. So why they have this 17 over 16 ratio, which is very high. I will explain that. Sorry. Yeah. So as we know that in the red giant or asymptotic giant branch star, like a sun-like star, we have the hydrogen is converting into helium, then helium converting into carbon, nitrogen, oxygen, and further we have aluminum, magnesium, silicon, and all the elements. So these elements are formed in the stars that we know. So we are basically stardust, we can say. Okay, so all these elements are formed within stars, and as the star is evolving in its lifetime, so our sun will become a red giant star after let's say 5 billion years, after 5 billion years, right? Similarly, the other stars which have higher mass than the sun, their evolution process will be different than the sun. And then if the mass is very, very high as compared to the solar mass, let's say, for example, more than 8 to 10 solar mass, this will go into a supernova phase at their later stages. Okay. So if the mass of the star is, let's say, 1.5 to 2 solar mass as compared to the sun, they have this uh, in the carbon, nitrogen, and oxygen, that is called a CNO cycle. We know. Okay. So during the CNO cycle, what happens is the 17 oxygen. I am talking about 16, 17 oxygen and 18 oxygen isotopes from the starting, right? So this they have this carbon and oxygen core, and then they have these different regions it has developed. Okay, the star when it is entering into red giant or asymptotic giant branch phase. Okay, the sun-like star but having higher mass. Okay, so they have this inert CO core, carbon and oxygen core, and then they have this helium burning shell, then helium intershell, and then different regions, different layers. Okay, and the outermost envelope is mainly made up of hydrogen. Okay, so this carbon and oxygen core and then we have this helium burning shell. Okay, so what happens is during some phase of the CNO cycle, the 17 oxygen within the core part is enhanced, okay, as compared to 16 oxygen counterpart. Okay, and then what happens is the convective envelope, which is the outermost region of the star, it cycles. So it goes into the inner core and then comes back, goes again and comes back. And this process is known as the dredge up process, right? And so what happens is when this convective envelope material goes into the core part, so this in within the core part, the 17 oxygen which was enhanced in the core part, it comes out and comes into the convective envelope. Okay, so the 17 over 16 ratio in the convective envelope or in the outermost part of the star will be higher. Okay, and then the grains are forming in the stellar outflows. So what happens is at some point, the stars are ejecting out some materials in the space, in the intergalactic medium or interstellar medium. So what happens is when these material is ejected out, sorry, yeah. So when this material is ejected out, that ratio 17 over 16 oxygen is there, okay, which is higher. And then when the grain is formed, within the grain, that 17 over 16 ratio will be higher. And this will be higher than the solar system ratio, of course, because the mass of the initial mass of the star is higher than the sun. Okay. So when the grain is formed in the stellar outflow, the 17 over 16 ratio is higher. So, yeah, so that you can see here in this plot, where you can see these grains having the higher 17 over 16 ratio as compared to the solar ratio. And then, yes, so this is the case. This is one grain which we had analyzed. It has the 17 over 16 ratio is about 2.2 times the solar ratio. And so this grain, you can see, this is the nanosims ion image. We can see this is the delta 17 over 16 ratio, which is about 1200 in delta value. Okay, this is the second one is the secondary electron image. The third one is the 28 silicon image, and the fourth one is the magnesium and oxygen image, 24 magnesium and 16 oxygen image. You can see here that this was the grain where you can see the center part, and there are three different surrounding. But this was a very interesting grain, but unfortunately this grain was we cannot find we could not find this grain in the second type of second analysis phase. Okay, so but we have this oxygen and silicon and magnesium isotopic composition of these grains. From that we can say that the grain ratio 17 over 16 ratio is about 2.2 times the solar ratio. So it will be somewhere here. So this is so it will be somewhere here, right? So this is the grain with the 17 over 16 ratio of 2.2 times the solar ratio and the solar 18 over 16 ratio. So this group 1 grain has a higher 17 over 16 ratio, but solar or close to solar 18 over 16 ratio. Okay, so this is the characteristic of group 1 grain. They are coming from red giant or asymptotic giant branch stars. The other grain, okay, so you can see here that the 17 over 16 ratio, which is, so we have seen that the 17 over 16 ratio is higher, but there is the limit that red giant and asymptotic giant branch star can produce 17 over 16 ratio. So how much higher? So there is a limit that stellar nucleosynthesis or the red giant or asymptotic giant branch star can create the 17 over 16 ratio. Just a moment, please. I have to plug in my computer. Okay, sorry. So this there is I was saying that there is a limit to this 17/16 ratio in AGB star. That is called the AGB cutoff, which is about 5 into 10 raised to minus 3. Now we have to go into again. Yes. So this one is a AGB cutoff, which is about 5 into 10 raised to minus 3. So up till now, so these grains are formed in the AGB stars. But AGB star cannot produce the 17/16 ratio, which is higher than that. Okay. And then, so we have to think about something else or different stellar source, which is the nova. So nova is basically a binary star where we have a binary star system where one star is a white dwarf star and another star is a normal red giant or asymptotic giant branch star. And what happens is the white dwarf star accretes the material from the red giant star. So when there is a significant mass accretion on the white dwarf, again the thermonuclear fusion or a thermonuclear runaway fusion occurs, which creates the 17/16 oxygen ratio, which is higher than the 5 into 10 raised to minus 3, which I was again showing in this plot, where we have this AGB cutoff and the grains, these region in the grain, group 1 grain, these grains are coming from the nova. So these are called as nova candidate grains. Okay. So, fortunately, in our study, we had one grain with 17/16 ratio, about 6.5 into 10 raised to minus 3, which you can see here in this plot. This red dot, which has 17/16 ratio, which was higher, uh, very high, about 17 times the solar ratio, which you cannot explain, right? And you can explain this using the nova nucleosynthesis. Okay, so this is the grain. You can clearly see that grain. So from after the nanosims analysis, this is the mass spectrometry analysis, which gives us the 17/16 image of that grain. And then this one, the second one, the down image is the secondary electron microscope or scanning electron microscope image, in which you can clearly see this grain, which is even less than 200 nanometers. Okay, so this grain is very, very small, but it is coming from the nova. Okay, so this was the another grain, and then the different another grain which we want to talk about, I want to talk about, is the group 4 grain. And this grain, another grain from Ishievo meteorite, it has the 18/16 ratio, which is very, very high. You can see 33 into 10 raised to minus 3. Now we have to go back into this plot. Yes. So this grain, Ishievo 6, you can see here in this plot, it is the 18/16 ratio, which is very, very far from the solar ratio. This is the solar ratio, right? You can see in the plot. And this grain is about 33 into 10 raised to minus 3. Okay. Or 3.3 into 10 raised to minus 2. So this grain is basically 16 times the solar 18/16 ratio, which you cannot explain in any of the solar system process. And you have to think that and this cannot be even explained in the AGB or RGB star. Red giant or asymptotic giant branch star also cannot explain the isotopic composition of this particular grain. So we have to think something else. So we have to see that this grain is coming from the supernova. And how do we know? So we have to do this analysis, which is called this supernova mixing calculation. So this is the image of a pre-supernova star. Uh, so we know that when the mass of the star is about 8 solar mass, 8 times our sun mass, what happens is the star develops different regions. So like in the core, there will be a iron and nickel, and then above that, there will be a region where silicon and sulfur will be created. So in the different parts, different nucleosynthetic processes are going on in the pre-supernova star. And what happens is it can so basically nuclear fusion reactions. Okay, So hydrogen converting into helium, helium into carbon, oxygen, and then oxygen converting into neon, magnesium, and then magnesium into silicon, sulfur, and then lastly iron. So it has developed different regions within the pre-supernova star, so up to iron. So after iron, it cannot further fuse because of the nuclear binding energy problem. And then when the fusion stops, what happens is the star will, the gravitational contraction happens and then it will explode. Okay. So when this explodes, the supernova, this is known as the supernova explosion. And when this happens, the different regions will be mixed together. Okay. And our grains will form in the supernova ejecta. Okay. After a few days. Okay. Okay. So, to explain the isotopic composition of this particular grain, 18 over 16 oxygen, which is higher than 16 times the solar ratio, to explain that, we have to see, so we have got about 8 grains from the supernova, okay? And then this one, the Ishiovo 6 grain, is about 16 times the solar 18 over 16 ratio. And for that particular grain, we have to assume that, or we have to calculate and then tell that the helium carbon zone, which is here somewhere, yeah, here. So the helium carbon zone, from the different zones in the supernova, the helium carbon zone produces very high 18 over 16 ratio. Okay, so the contribution of helium carbon zone to explain the isotopic composition of this particular grain, which is the Ishiovo 6 grain, which is about 16%. Okay, and so almost 16%. So this is the highest fractional contribution which we have to take from helium carbon zone to explain the oxygen isotopic composition of that particular grain. So similarly for other grains, which I will not discuss. So this is the problem which is known as the zone mixing in supernova ejecta. So still the mixing in supernova ejecta is not very well understood, and by analyzing these particular grains, silicates and oxide grains, we can constrain the supernova mixing models. Okay. Okay. This is the another interesting thing that I wanted to discuss, which is the grain condensation. Okay. Uh, yeah. So to find the, or to analyze the structural and chemical composition of these grains, we had to use the entirely different instruments and methods, right? Which is known as the scanning and transmission electron microscopy and transmission electron microscopy. Okay. And for the transmission electron microscopy, we have to prepare our sample, which is called as the thin film lamella. Okay, so the thickness of the grain should be about 100 to 150 nanometers. Okay, and for that we have to use another instrument which is called the focused ion beam. This is the focused ion beam, where we are using the gallium ions to prepare our sample. I'll not go into the details of this grain, but we will so we'll take the sample, our meteorite sample, and then we will cut the different parts, the surrounding parts, and then we'll put the cap, and finally we get the which is called the thin film lamella, which we put it in the transmission electron microscope to get the structure as well as the chemical compositions of these grains. Okay, so for example, this grain is about 200 nanometers across, okay, which you can see here in this image. Okay, I want to talk about a unique grain which is known as the calcium sulfide grain. So out of the 8 to 10 grains that we analyzed for structure and chemical composition, one grain was very interesting. So we had this calcium and sulfur on the top of the grain, and then below that particular grain we had the enstatite, which is a silicate grain. So to know, and then this particular grain is coming from the J-type carbon star with the oxygen rich atmosphere. This is an entirely different stellar source. where it is a carbon star but having a oxygen rich atmosphere, where this particular grain might have formed. Okay, because the isotopic data of this grain suggests that this grain was formed in the J-type star. Okay, and then from the chemical composition, we can say that this calcium and sulfur rich grain, which is a calcium sulfide or oldamite, and we have proposed that this grain, calcium sulfide rich grain, was formed first in the J-type star, and then later on the enstatite or the silicate grain was formed. So this is a like a complex grain having a different formation as well as the alteration history. Okay, so these are some of the key takeaways from this talk. I'm almost finished for my talk, and then we have the isotopic study of meteorites. So these are the key takeaways where these meteorites give us clues for the formation timescales that we have seen in the earlier slides, that our solar system is formed about 4.56 billion years ago. And then isotopic analysis of these pre-solar grains, basically silicates, oxides, or silicon carbide grains, give insights into the different stellar nucleosynthetic processes which are going on in the RGB or AGB stars, nova, and supernova mixing or supernova processes. Okay, so we can get insights into these different stellar nucleosynthetic processes by analyzing the isotopic compositions of these pre-solar grains. And then by structural and chemical compositions, we can get the insights for the formation as well as the alteration histories of the presolar grains. So these grains are formed in the stellar outflows or in the supernova ejecta. So from the formation to the alteration, and then from the lab analysis, we can we can tell the total entire history of the presolar grain. And then the combined isotopic, structural and chemical analysis of the presolar grains gives us clues about the alteration in the protoplanetary disk. And then simulations of these protoplanetary disk environments can further give us insights into the, the planet formation. Okay, thank you so much.
Thank you, sir. It was really an insightful session. Actually, never thought about that from meteorites, what much more information we can gain, actually, because we have just been knowing that collecting meteorites is a hobby for some and a science for some. But
Yes,
what science can be done from meteorites is really interesting. This is what you have shown, and it's really intriguing. Uh, yeah, I would open
thank
the
you, ma'am.
floor for the questions.
Sure.
Anyone has any questions, please can switch on their mic and please go ahead. Any questions?
I hope I have explained it so that different, so the people are coming from different backgrounds as well as different, age groups. So I hope I could explain it.
Yeah, definitely, sir, because it's really interesting. Sir, Ankush has a question. Yeah,
Sure.
Ankush, please go ahead.
Mm. Hi Manish, very nice talk. So I have one question. This pre-solar grain,
Yes,
uh, what is the exact age? Can we determine there like 4.5 billion minimum? But
yes.
are they like 6 billion, 8 billion, 10 years? Anyway, can you estimate or anyway we have knowledge about it?
So people actually have tried to estimate the age of pre-solar grains,
Mm-hmm.
but it is a, again, it is a very challenging thing to do. But I guess it is so beyond the our solar system formed. It is, so as far as I know, it is about 1 to 1.5 billion years before the formation of our solar system.
Okay, that is the
Yeah,
age.
that is the current. Yeah, but it's not for all the pre-solar grains, right? So the
Ah,
people have tried different isotopes and different
mm-hmm.
samples. So for
Mm-hmm.
their samples and for their isotopic systems, This was the age. It's a very challenging work, and it's a very small amount of work has been done to age these presolar grains, so to determine the ages of presolar grains.
Yeah, but what method they use generally to
Again,
estimate
the
this?
isotopic
Iso
composition. Yes,
that is the only way, right?
yes, yes. I
And
think
are
they have
they?
used what we call it noble gas isotopic compositions.
That is the way. Okay. And do they coming from the same star or dead star, whatever, sun before sun? Are they corresponding? I mean, source is same nebula from where it is coming pre-solar grain, or can you have like some J-type star, some different star, and
No, no.
mixed up? Do you see?
Yeah, so I have explained that these three sources, but there are many different sources. Like
Oh,
it can be J-type star, or it can be carbon star, or it can be Wolf-Rayet star, or it can be supernova, nova, anything.
it could be mixture. Okay, okay.
Yes, yes, yes. No, but one
Right.
particular grain would have come from, so the
Single
isotopic composition of one particular grain would have come from a particular star, but then
star.
again, that is a question. So
Hmm.
when there is a supernova star, it has injected some material where the isotopic composition is different, and then again it could have been processed in the AGB star,
Oh.
another star. Yeah,
So it could give multiple process
yes.
and multiple
So
epochs in
yes,
so okay.
yes,
Interesting. Yeah. Thank you.
yes.
Thank you, Ankush. Anyone else for any questions, please? The floor is open. I think so, Manish Sanghani, sir. This was a really technical talk for the people over here, our audience here. But yes, definitely, it's a talk where we can deep dive into things which we actually never thought of. For
Yes,
like people like me who are interested in meteorites, but yet we just look for the Geminids or Leonids or anything, and
yes.
we
And
really don't know how to find them on Earth. We have no clue how to look for the actual meteorite which has fallen on Earth. And
definitely.
I have read many a times that Rajasthan is a very good source for collecting the meteorites because it
Yes,
has sand.
yes,
So the thing doesn't get depleted, or the meteorite fall doesn't get vanished off. So
certainly. Yes,
yeah, definitely. The talk which you have given is really insightful, and uh,
thank you.
definitely we will be in connect with you to learn more from you. Definitely, sir.
Definitely. Yes,
Thank
yes.
you,
I
sir.
would be delighted. Yes.
Thank you so much, sir.
Thank you so much,
Yes,
ma'am. Thank you.
yeah. Jitender,
Um, I would request everyone, if you're having any doubt, okay, just don't hesitate. Like sir, just going to talk in like high level
Yes,
languages.
yes. Please don't
Please,
hesitate
just
to
don't
ask
hesitate,
questions.
everyone. If you have any question, okay, if you're having this school type of question, also just don't hesitate.
Yes,
Okay,
yes.
question doesn't have any level, so you can just raise your hand and you can just interact with sir directly. If you want to know about any projects, if you want to need, or if you want to know anything about the related topic, you can just ask. So just raise your hand. Just don't hesitate, everyone.
Yes, students.
sir, I would like to ask you one thing. We got some stuff from asteroid Bennu,
Yes,
right?
yes.
And did you or your team got to collect have that sample with you and do some science out of it?
Actually, some of my collaborators, they have got the samples because the samples are very precious,
Definitely.
and there is a like I can say hell lot of competition to get the samples.
So have we got any sample from moon also?
Yes, so yeah, I have worked and I have trained in PRL, which is a physical research laboratory, a part of ISRO in Ahmedabad. We do have moon samples, and I have analyzed several moon samples also from Apollo missions.
And it is definitely said that the moon dust is really very what we say, it sticks to the whatever it comes in contact with. Is it so? It's very fine.
Yes,
Regularly.
it is a fine grain particles. So these asteroid primitive, sorry, I think okay. So these primitive asteroids and like for example, you are telling about Bennu. It is also kind of a rubble pile or like a, very fine,
Yeah,
dust
yeah,
grains or dust
yeah,
particles sticking together.
definitely. So Mohammed Azhar has a question. Yes, Mohammed, please.
Yes.
Sir, what is nebula rose?
Sorry,
What is nebula rose? Nebula, how to create nebula?
nebula.
Yeah.
Nebula is basically a remnant of so like for example, I have explained in my slide, one of my slides maybe, that there is a supernova explosion, right? And when the supernova explosions happen, or when the star dies, there will be a remnant of that star around in the interstellar medium. So basically, that is the nebula.
Okay,
Where
sir, I have another question.
there will be a
What is
gas and dust around the star. Yeah.
okay, sir, okay, sir. I can ask you another question. What is biggest star, sir?
Sorry,
How to
I'm not
create
able to.
biggest star?
I'm not able to, understand the question. Hello.
Mohammed, I would request you to kindly write your question in the
Maybe
chat
yes,
box.
yes, yeah,
Yeah, because we are not able to get you because
yes,
of the bad network.
yes. There is a problem in the network, I guess.
Yeah.
Is there
So
any?
there is
Uh,
one more participant with a question. Yes, please go ahead.
yes, one.
Hello, am I audible?
Yes,
Yeah, yeah, you are.
Yeah, good evening, sir. I
yes.
have doubt about, regarding pollen, like these grains. When we talk about pre-solar grains, anything, any object or any particle which have been existing before our solar system formed and it's still in its original form are called pre-solar grains, or are there any other specified criteria or conditions to satisfy to call as pre-solar grains?
That's a good question. So I guess the definition says that the pre-solar basically means before the sun. Okay, so whatever is formed before our solar system or our sun is pre-solar. Okay, and
Like,
it has to. So the isotopic composition will be definitely different than the solar system.
like basically what we observe is there are many kind of different compounds or compositions which we found in our solar system which been from a really lot areas, like from different patterns,
Yes.
like basically what we see there are different type of things. For example, what we think even is like water on earth is not the actual, it's a pre-solar like thing which has been existing before, since before solar system formation. So like my question is, are these particles exactly like defining our true nature of the universe, or are they kind of just particles roaming around in universe?
So, so like I said, what happens is when we know the history of our solar system, right? The sun was formed before about 4.6 billion years ago. Okay, so but from starting of the Big Bang, so which occurred about 14 billion years ago, right? So within a few million years, there was a star formed. Okay, and then so we have the several generations of stars. So we have population, so different stellar populations. So okay, so initially different kinds of stars which were having only hydrogen, which were made of only hydrogen. Okay, and then so when they formed and when they died, they expelled some other elements like helium, carbon, nitrogen, and then so like when you go from starting to the up till now, so we have several generations of stars, and when the star dies, it ejects out material in the interstellar medium, right? And from that interstellar medium, again, after some millions or billions of years, again another star will form. Okay, so it has the composition of the previous generations of stars, right? And again it will form, it will live its life, and then again when it will die, it will expel out material, because our universe is so big, right? You know, so again it will expel out some material in the interstellar medium, in the surrounding, right? So this is a continuous recycling of gas, of dust, of particles and everything.
Okay, and my last question, like when we specifically study about pre-solar grains, like what
Yes.
if like a asteroid or any object or any particle has been influenced by different sources. For example, there's an asteroid which chemical composition or top layer or like topmost layer of the study is been influenced by any previous thing or any previous situation happened to it, like an
Yes.
asteroid been to a different solar system and cause of any chemical reaction or aging factors, its composition or compound might have been
Yes.
changed.
Yes.
So like how we determine exactly how old is that or its exact composition and like characteristics.
So, like for a determination of age, there is a entirely different method which is called the isotopic analysis or isotopic composition of. So people have used different isotopic compositions. I have not determined the age of these particles because it is very different, difficult, and it is a very precise method. You have to use, you have to take care of many different things. But about the chemical composition, it could be different, right? Because we are getting different kind of presolar grains, like I have explained in my slide. There are different phases. I mean, we have silicon carbide, we have oxide, we have nitride, we have silicates, we have diamonds. Okay, we have different kinds of presolar grains, and the chemical composition can be altered, as well as isotopic compositions can also be altered, but in a way we are assuming that the isotopic compositions of these presolar grains are more or less intact. They are not changed much, and that's why we are seeing them in the like I have explained that the isotopic composition is this much higher, right? So they basically have retained their isotopic compositions.
Okay. Like, and what if the composition or like its chemical formulating have been changed to its aging or like throughout the year or throughout the time its compound might have been changed, right?
It can change. The nature is hello.
Yeah, you are audible, sir.
Okay, so it can be changed. Like the isotopic, I said the chemical composition of these grains can be varied or can be changed by different processes within the solar system, in the protoplanetary disk, on the meteorite parent body, or even on Earth, right?
Right. So the next question can be taken up from Bharti Senthil Kumar.
Yes.
Hi, sir. I'm Bharti.
Hello.
Yeah.
Sir, I'm pursuing BE in aerospace engineering. And after listening to your talk today, it was really, really interesting to know that we can actually research about real remains instead of just seeing through telescopes. So I was wondering how can an engineering student pursue this, or how can we work on these kinds of projects too?
Okay. Uh, that's a good question. So after you finish your engineering or graduation, you can join as a master's student in some of the universities where you can take courses like in astrophysics, or you can take courses like in planetary sciences or something, and then you can do PhD. So this is a career path that can be done, right?
Okay.
That can be
I have
taken.
another request to sir.
Hello.
Would it be possible to, am I audible?
Yeah,
Just
yeah,
a
you are.
moment. Yes. Can you please?
Can we get in? Uh,
Hello.
Yeah, Bharti, please go ahead.
Can we get an opportunity to intern under you or get an opportunity to learn more about your kind of projects?
There are several institutes work in meteorites in our country, like this PRL, Physical Research Laboratory. Okay, this is the main core part where we study the planetary materials, and several others might be IUCA or IISC. They might have this thing, and in abroad there are several many different institutes, and you can even get the position as an intern. Yes, it is possible, but you have to look into a proper place.
Thank you very much, sir.
Yes.
And at the beginning, you were feeling a bit sad. I think that you weren't able to cover many age groups, but even I was able to understand what you said. So I wanted to be very thankful for that.
Thank you so much.
So see, this is the impact of our students, the speakers on our students. Actually, our students are widespread, and our speakers are also all from different fields, and they really are encouraged to listen to different kind of talks. They are really interested in different fields. So the speakers as well as the students, they get a very good interaction when in the session.
Yes, definitely.
Really,
So this is that's what I was telling to Jitendra, that this is a nice platform that you have created, where people can interact, and maybe later on we can collaborate with each other to do
definitely,
something
sir,
else.
definitely.
Yes.
Sir, I would also like to ask you one thing. Like you said that the composition of that pre-solar grain could change with time. It could
Yes.
be hampered by some natural phenomena which is
Yes.
occurring in the
Yes.
interstellar medium.
Yes.
So,
Yes.
so how actually can we very precise that from where has it come? Where was it originated from? uh, do we calculate the place from where we have received it, or do we calculate the place from where it has originated?
Yes, so that's why we are doing this isotopic analysis, which is different than
Yeah,
the chemical analysis, right? So, like
yeah,
I explained it in my several of my previous slides, that like there is a fixed value of the solar system ratios, right?
yeah.
And if it is very different, then it has to be coming from something else, like
Okay,
some other stellar source. It cannot origin in within the solar system, and
okay.
and so that's why we are doing this isotopic analysis. Whether it is very different than the solar system, then we can correlate, or we can we will have to look into the different models. So, like, we have synthesis models of AGB stars. We have nucleosynthesis models of supernova, nova. So we can take both the things in parallel, and then we can correlate that these particular isotopic compositions would have come from this particular star.
Definitely, definitely.
So we are assuming that these are not changed, and we are actually seeing experimentally that these isotopic compositions have not changed, but chemical composition can be different, because when
Right.
the grain was formed, there will be some chemical composition, but it can be different when, so let's say, for example, when it is coming on earth, and when so we have this environment where it can the grains can be hydrated, right?
Hmm.
So it,
Hmm.
it can interact with the surrounding environment, and then
Its
oxygen
chemical
can,
composition changes.
yes, chemical composition can be changed. Yes.
Right. So the next question coming up from Ajay Mehta.
Uh, yeah, hi, Manish. This is a very great presentation for a complex subject. I just had a question. The uh, you get the sample from the meteorites which are coming down here to the
Yes.
Earth. So as they make entry into the atmosphere, they go through a very tremendous temperature.
Yes.
Do you think that that has any impact on the composition, chemical or the isotopic composition, and how can you account for that?
Yes, that's a great question. So yeah, when the meteorite enters in the Earth atmosphere due to friction, the surface layer of that particular rock will be burnt. So you can see the fusion crust of that particular sample, right? The black crust that you can see. But
Mhm.
within, so when you are analyzing within the sample, when we are getting the samples from within that particular sample, then the again the chemical composition might have altered a bit, but the isotopic composition does not change that much. So that
Okay,
when we analyze, yeah, so we have to go through different phases of chemical, sorry, not chemical, but we have to go through different stages of sample preparation where we cut, so the surface layer or the surface part, we cut it, and then we take the inner part which is intact.
okay. Yeah, that uh, I have another question which is not probably not related to, well, it's definitely not related to your work, but I'm wondering if you are aware of, within Earth itself, we say that there is a tremendous evolution in the chemical composition as with the
Yes.
time,
Yes.
like there was no oxygen or very little oxygen in the beginning.
Yes.
Now, do you know if anyone has actually taken any samples from the deepest part of the ocean, like in Mariana Trench, and see how the composition compares with what we see here?
Okay, I guess people must have, taken sample from the deepest part as well. But I'm not very well aware that what are the compositions and what are the isotopic composition will be somewhere within the solar system. But I'm not sure what type of chemical compositions would have been there because of the higher pressure, because the pressure is very high
Mhm.
down the Mariana Trench or whatever is the depth is about 10 kilometers. So yeah, so the
Yeah.
pressure and temperature conditions are very different. The light is not reaching there, so there must be different kind of, we can say, evolution of physical evolution of even even the living organisms as well as the non-living samples.
Right. Right. Yeah. So what I was wondering is because we look at the universe and there is so much to find, but even within our environment, there are areas that we are totally unaware of many times. A
Yes,
great
yes.
presentation. Thank you so much. It was very clear for a complex subject.
Thank
Many
you so much.
congratulations.
I would add to your question. So I have read somewhere a couple of days ago that there are some sites in Russia that they have started drilling within the Earth's crust. So they have gone deeper. I forgot the the numbers, how deep they have gone, but then they have to stop because the temperature and pressure conditions are so high that their drills were not working.
Real melts.
Yes. So
Thank
people
you.
are doing different kind of experiments. Yeah.
Thank you.
Yes.
Okay, sir. Thank you. And the next question coming up from Rahul Das Gupta.
Yes. Hi,
Hello.
Rahul.
Hi. How are you? Nice to see you after
Yeah.
a long time.
Thank you.
Firstly, I would like to say that I saw how much hard Manish Bhai worked to separate these Presolar planes. It was days and days of work. He used to work day and night. It was very good.
Actually, I forgot to mention that the nanosims times that I have analyzed is
We were
very high. Yes.
yes. It was a lot of hard work. I mean, then so I
Thank
mean,
you.
so what was the success rate? As in, like, if you chose any meteorite, would you find Presolar planes, or like would you choose some specific meteorites to get a good number of Presolar planes?
Well, I guess if you take any carbonaceous chondrite, then there is a chance that you will get some amount of presolar, material.
Okay, okay, good, good.
But then again,
Yeah.
what procedure that you are following, whether you are doing the chemical separation or you are doing the, in situ map that I have used in my PhD work, that will be again different. I mean, the success rate.
Okay, okay, okay. I mean, the solution and in situ work might give different results. That's what you mean. Right?
Yes. So, but
Yes.
the problem with the chemical separation is it is also a very long process, and when you miss some stage or you do something wrong, then there will be
Yeah.
a difficult. But in situ work again, you have to sit on the nanosims. We can automate a few things. You have used nanosims, so
Yeah.
we can automate a particular thing. But then again, the source failure and many things happen. So, but I guess in situ work.
It's
So
better.
once the chemical separation is done, you are king. You have many presolar grains, like Kuljit ma'am samples that we are still using. We have our mentor, ma'am, and other people. I would like to thank Kuljit madam. She is from PRL. So she has done a lot of work and she is my mentor. So she has done a lot of work in presolar grains. So they have analyzed a few, so they have extracted a few silicon carbide grains from meteorites, and we are still using those samples. So this is how.
Yeah.
And yeah.
Good, good. Thank you. And just a different question on the isotope part. I mean, just trying to understand your 17 diagram.
Yes.
So the first vein that you talked about was on the 17 axis right up there.
Do you want me to go to the slide? Yeah.
And I think you discussed two cases, right? On that, one was high 17 and one was high 18.
Yes. So we have mainly got the grains from group 1 and group 4. Yes, mainly.
Group
There was
1.
one grain from.
Okay.
There was one grain from group 2, but others are mainly from group 1 and group 4.
Okay, so I just wanted to understand the genetic implications of the different groups of presolar grains. So the first one that you said was the dredge-up mechanism, right?
Yes.
Dredge-up mechanism was for the group 1.
Yes.
And the one which had the high 18O, that was from the Ishiovo. That what was the explanation for that?
So that is coming from supernova. So we have explained this isotopic composition using the mixing models within the supernova.
Okay. Yes,
Yeah.
yes.
And the another one was nova. So there is an AGB cutoff that you can see here. So yeah, so AGB AGB star can only produce up to this part. So 17/16 ratio, 5 into 10⁻⁻3. Beyond that, you cannot produce 17/16 oxygen that high. So we have to see into different, and then so we have taken these different nova models. So we have different types of nova, CO nova and other types of nova. So we have mixed the nova material with the solar-like material to explain this isotopic composition.
Yeah. Okay. Good. Thank you. Thank you for the nice talk. It was nice to be here. It is a nice
Thank
initiative.
you so much, Rahul. People who are joining, Rahul is my colleague from PRL. He has also done work in PRL along with my side, and then he is right now. So he has also done postdoctoral fellowship in Africa. I think South Africa, Johannesburg, Cape Town. Yeah. And he's also expert in this kind of thing, using and analyzing extraterrestrial samples.
I was more into after the sun is born, so you are more behind in time. But I was
so we have both kind of experts with us. One is pre-solar and one is post-solar.
Post-solar, yes, yes.
Maybe Rahul, you can talk to Jitendra and
I
talk in this
Definitely, I
forum.
was just going to say that only, sir.
Yes,
yes.
yes,
I'm here only. I'm inviting you as a speaker, sir. For
Sure, sure.
yes, yes, yes.
Sure.
I would ask for your contact number from Manish, sir. I'll definitely contact you.
Sure,
Yes.
sure, no problem. Yes. Yeah.
Okay, sir.
That's
Thank you.
really
Thank you,
nice.
Rahul, for
That's-
attending my talk.
Thank you for the invitation. I mean, I was not aware of this, so if you had not,
Yeah.
I would have missed it. But it's good to know. Yes.
Yes.
Thank you. Thank you.
That's really nice. Really nice to have friends on board.
Yes, 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 definitely.
Yeah. Sir, by any chance, PRL must be in connect with the GSI to get the samples of meteorites, right?
So PRL has its own repository of meteorites.
Okay.
And so what happens is, so during my, when I was doing my PhD research, I did it from Denmark. So our, means my PhD supervisor, they also had these meteorite samples. So
Okay.
different universities have their own meteorite samples. I'm not sure whether PRL writes to GSI for the samples or I'm not quite sure about it.
Actually, sir, like we live in Rajasthan, and Rajasthan has a very large area which is extremely barren and vacant.
Yes.
So whenever there is a meteorite fall, like the Geminids are going on, so
Yes.
whenever there is a meteorite fall, how do we actually detect them, and how do we actually come to know that where precisely we can find them? There must be some method for that.
I mean, I myself haven't gone to, field
Okay.
to collect the meteorites.
Yeah.
So, but I can ask someone who has gone into the field and collected meteorites, and then
Yeah. Because,
let you know.
because I am really curious to know that how do we actually differentiate from a normal rock and from a meteorite?
Yes.
Theoretically, we know that a meteorite
Yes,
is much
yes.
heavier. It would be a charred stone. It would
Yes.
be somewhat dark in color, or it would
Yes.
be somewhat smooth on the surface. But
Yes, yes,
when you actually go out in the field and look for the stone, a normal stone and a meteorite, how do we
how
actually
to- yes,
differentiate
yes.
it? And where to look for?
Yes,
Because
yes.
living in a place like Rajasthan, we definitely can come across some things like this, but we
Yes.
hardly know about how to identify. So
Yes.
I was just curious to know about that.
Yes, 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 definitely. I'll get into touch with you, and then maybe I can provide you with some more detailed information on
Thank you, sir. Thank
meteorite
you.
expedition. People from in the US, people from Arizona University, and they actually go into the Antarctica, and they have
Yeah.
the mission to
Yeah.
collect the meteorites.
Yeah, there is a mission from
Different
India
methods.
also, sir. It's from India also. One mission of women's, mostly about 7 women, go to Antarctica each year to find the meteorites. I have heard
Okay.
that from someone.
Okay. Okay.
Yeah.
Maybe I'm not very aware of our Indian mission.
Okay. Okay. Really, thank you, sir. Thank you so much for
Yes.
giving such an insightful talk about the pre-solar grains and how to analyze all those things. It's really technical, but yes, we got an idea about how the
Yes.
procedure is being done. So it's
Yes.
really nice to have you on our platform. Really thankful to you. And one last note, I would request all the participants over here to please switch on the camera for a group photograph.
Everyone, please turn on your camera so we could just capture this moment, as we already like we do for every session. So please, everyone, not 2 or 3 people. Okay. Nice.
I must thank Jitendra and Amoli ma'am and the Propagation Institute to create such a nice platform, and again for inviting me to participate and give a talk. Thank you so much.
Most welcome, sir, and we would like to hear from you more. Definitely.
Recently, another paper from my collaboration with PRL has accepted in Astrophysical Journal, where I mean the experiment was done at NASA, but we had done this chromium isotopic compositions in presolar silicon carbide grains. So it will soon published in APJ.
Wow, that's nice. Yes.
It's really nice, sir. Congratulations. Like before publishing that, congratulations.
Thank you so much.
And thank you so much, everyone, for joining us today. And I would like to say once again, Rahul, sir, please connect with me so we could just discuss about your schedule. Whenever you're
Yes,
just going, I'm inviting you from here only. And
Yeah, but I need time to prepare also. I mean, at least 2 weeks.
yeah, it's okay, sir.
Definitely, sir. Definitely. That topic would be of your choice. The
Sure.
platform would be ours.
Okay.
Yeah.
Yeah, that's a nice thing. Rahul can also share his work.
I will be
He's
happy to
expert
speak.
in Teams, right?
Yeah, in PhD I worked on TIMS, and then I moved to in situ geochemistry more. So yes.
Okay.
Okay. Okay, thank you so much, sir. Thank you so much, everyone.
Thank you,
So,
everyone.
bye. Bye, everyone. Have a nice
Yeah.
night.
Thank you so much.
Okay.
Have a nice evening, a nice good night sleep. Bye.
Thank you. Thank you.